Alright, so this is 8.13, the last section in Chapter 8, in the second to last section of our Unit 6. This section is going to talk about molecular structure, which we'll call the VSEPR model, VSEPR model, and that stands for Valence Shell Electron Pair Repulsion. Essentially what this is it's telling us what is the actual geometry of a molecule. Molecules aren't two-dimensional things. They're three-dimensionals, just like you and I and the computer you're in front of and the pencil that you're holding. So we want to know what actual structure a molecule takes because, as we have found out, the structure of molecules greatly affects their properties. The structure around a given atom is going to solely be, well, not solely, but mostly be determined by minimizing electron pair repulsions, or getting electrons kind of as far away from each other as possible, because as we know, electrons really don't like each other. And so let's take a look at a Lewis structure of methane. So this is methane, but if you'd be able to see a methane molecule, if you'd shrink yourself down to the size of a methane molecule, you wouldn't see this. You specifically wouldn't see this two-dimensional geometry. Instead, you'd see a three-dimensional molecule that actually would look like this. Okay, with the blue dot in the center being the carbon atom and the reds being the hydrogen atoms. Now there's an issue with this type of model that I have in the middle of the slide. It's difficult to draw. I'm not a good artist at all, and I don't expect you all to be, although you're probably better than I am. And yet, you know, we're not going to draw these molecules. They just take too much time. So there is another method that we'll use to draw three-dimensional molecules, and it's the dashes and wedges method. Bring up a third picture here. All right, so that is the methane molecule drawn with the correct geometry. And what I want you to notice that a wedge symbolizes a atom coming out of the page at you. So this hydrogen atom would be the same as this hydrogen atom. And then a dotted line or a dashed line kind of symbolizes an atom going into the page. So this hydrogen atom would be the one that's going into the page right here. Now, what I haven't shown really all that well, you can probably make an argument that this hydrogen atom is also going back into the page. But if I would just kind of rotate this molecule, the structure, you'd see that it would be possible to get that guy and that guy in the plane of the picture, where this guy and this guy are going in and out of the picture. So we use the dashes and wedges model to show that three-dimensional structure. That is actually the structure of the molecule. Now obviously methane isn't the only molecule you're going to be worried about. There are a lot of different molecules that have different structures, so it's going to be important to figure out how to draw those structures. So here's a few steps to learn how to draw VSEPR models. First of all, draw the Lewis structure of the molecule. So see how many total valence electrons there are, place bonds and atoms around a central atom, and then satisfy the octet rules and draw your Lewis structure, any remaining electrons in the central atom. Next, count the electron pairs and arrange them in the way that minimizes repulsion. So if you have 6 electron pairs, now what's electron pair? Okay, electron pair encompasses both a bonded electron pair and non-bonding electron pairs. For water, for example, if you want to draw the water molecule, H2O, oxygen here has 4 electron pairs. Okay, it's got 2 lone pair electrons and then 2 bonded pair electrons. All right, so understanding those numbers, that there's 4 electron pairs, is going to help us be able to figure out the geometry of this particular molecule. And the water is bent like this. That's what gives it its polarity. And we know that because these electrons right here are pushing down on the hydrogen atoms, causing that bend. Alright, so step 3 then, after you're done counting the electron pairs and arranging, is to determine the positions of atoms from the way the electron pairs are shared, so the way the bonds are shared in the surrounding atoms. And then the final step in this process is to determine the name of the structure. That's probably the most difficult step, just because it involves memorization, and you know my views on memorization. Alright, so let's look at a couple of examples here. The first molecule is a rare one. Actually, the first and second are pretty rare examples. A linear molecule, so one that's in a straight line. be an example of BeCl2, so barium chloride would be an example of that. Barium often forms a incomplete octet, so only having the 4 electrons associated with it is going to make it happy, and so it forms a linear molecule. One that you're probably more familiar with is carbon dioxide, but I didn't want to draw that one first because it involves double bonds, and that freaks people out sometimes. And also, you will see that it doesn't adhere to this rule right here, number of electron pairs. Now, because you're going to say, well, there's more than 2 electron pairs. But one thing we'll learn later on is that double bonds don't count in that number of electron pairs. So there's actually only 2 electron pairs, 1 and 2, right there. All right. So that's a linear model. Let's go now to the trigonal planar model, which is that second one. And again, these are names right here that you're going to have to just do a lot of practice problems with, and eventually they'll kind of absorb into your brain. Trigonal planar has a central atom. Let's say boron is our central atom, and then 3 atoms that are around it. And so this atom too doesn't have a ton of 3-dimensional structure. Everything is in the plane of the picture, trigonal planar. Okay, boron, another one of those atoms that can form an incomplete octet. All right, now a little bit more familiar, maybe to us, is the next one, a tetrahedral. All right, in that molecule you just saw on the previous page, that's methane. Okay, so we've got CH4, that's methane. Remember, I drew that with the dashes and the wedges. Wedge coming out of the page. H. Dashes going into the page. Careful with that line, it makes it look like chlorine a little bit. Okay, there you go. You got CH4. All right, now that's what we call molecular geometry, the geometry of the molecule. I want to note one thing here, that molecular geometry isn't always the same as what we call electron pair geometry. And let me show you 2 examples of that. All right, the CH4 molecule, which I just drew. Let's put that up there again. CH4. Just like this. All right, oops. Let me go back. And here. There it is. That's CH4. And we call that a tetrahedral molecule. Okay, that's tetrahedral. It's tetrahedral in both electron pair geometry and it's tetrahedral in molecular geometry. All right, but the next guy that I'm going to draw is not going to be tetrahedral in both. I'm going to draw ammonia. All right, ammonia. Ammonia is NH3. Central atom is nitrogen. Okay, and we've got a hydrogen here. Actually, a hydrogen coming out at us, and a hydrogen going back into the page. And if you do the Lewis structure correctly, you'll find out that there's actually electrons up here as well. So what we see is that these electrons are kind of an analogy or similar to that hydrogen atom right there. And those electrons have kind of forced the hydrogen atoms downward, forming that tetrahedral structure. So we have a structure up here, and then one there, this one here, and then the one going back into the page. So we have a tetrahedral structure. So this is tetrahedral as far as electron pair geometry goes. But when you talk about molecular geometry, well, for molecular geometry, we don't really care about those unpaired electrons. We care about what the molecule looks like. So that's actually got a different structure, and we call its actual molecular geometry, we call it trigonal pyramidal. And ammonia is very common. You'll do a lot of work with it, so that'll come pretty easy to you, I think. All right, so let's look at some other structures now. See if I can go back for a second. Yep, okay. Let's look at some other structures now. Some over complete octets, you may say, give lens to these two structures, trigonal bipyramidal and octahedral. Trigonal bipyramidal, maybe an example here would be PCl5. Okay, you know, phosphorus creates some issues and can have an over 8 structure, over octet structure. Octahedral, maybe that would be like SF6, sulfur hexafluoride. Okay, sulfur does kind of the same thing as phosphorus, giving that over a octet. All right. So octahedral structure, it has six atoms bonded to that central atom. So 1, 2, 3, 4, 5, 6. Again, trying to minimize those electron repulsions. All right, and a couple more now. Oh, these are kind of relating back to some of the other ones that we saw. There's the tetrahedral again, the trigonal pyramid in the middle that we saw with the ammonia. And then one of our most famous ones is the bent, and this is what water would look like, obviously. I think these three are some of the more common structures that we'll see. Tetrahedral, trigonal pyramid, and V-shaped. We'll deal with these quite a bit. And some very uncommon ones are these four, trigonal bipyramidal, seesaw, T-shaped, and linear. Seesaw structure would be an example of like selenium, be like selenium tetrafluoride. Okay, if we look at that structure, we'd find out that there's 34 valence electrons there. And so when we would draw it, we would notice that just by circling selenium with fluorines isn't enough to satisfy all the electrons needed, so we need to put an extra pair of electrons on the selenium. And what that does is it forces the fluorines downwards into this seesaw structure. So these electrons right here are that lobe right there, forcing them downward. So this is the electron pair geometry. There's the molecular geometry right there. Okay. T-shaped, also an interesting one. Chlorine trifluoride would be an example of a T-shaped molecule. Again, if you were to count the valence electrons needed, you would notice that there are 4 electrons unaccounted for, so those 4 electrons have to go on the central atom. And again, that pushes those fluorines down in the direction that we see. Now, what happens with these electrons, you actually have 2 of the electrons going back into the page, and you have 2 of the electrons coming out of the page, okay, to give us the minimal repulsion. So it looks like that, and that's what gives us shaped. And then the last weird one we've got on this page is a linear, and I'm actually going to use a polyatomic ion to show you the linear. That's the triiodide ion, 3 iodine atoms bonded together, pretty common ion. And again, if you do the electron arrangements with triiodide, you will notice that there are 6 electrons that need to be tossed on that central ion, or central atom. And that gives us that linear structure that we see right there. Okay, so those are some very different structures. Now, there's a lot of stuff to memorize, I understand that. So what I'm going to do is I'm going to post this sheet that you see on the right side of the page here onto Edmodo. If you want to use that for your homework, if you want to print it off and use it for your reviews, you can do that. Note that this chart is not provided on the AP exam. You just have to know how geometry works, how electron pair repulsions affect geometry, and you have to know those geometrical names. I'm assuming they stay pretty common with trigonal bipyramidals, trigonal pyramidals, tetrahedral, stuff like that. So they're not going to try to trip you up. But they are going to ask you, I really think they're going to ask you to predict the geometry of the molecule from the electrostatic repulsion. So don't let the big terms fool you. Electrostatic, just electron repulsions between bonding and non-bonding pairs, so bonding electrons and non-bonding electrons. Let's do a couple examples then before we stop here. I want you to determine the shape for each of the following molecules and include bond angles. Okay, bond angles were with that prior cheat sheet. We've got HCN, we've got hydrogen cyanide, we've got PH3, phosphorus trihydride, and SF 4. Okay, and I'm just going to do one with you here. Do HCN. First thing, let's draw that Lewis structure. Total number of valence electrons, we've got 1 plus 4 plus 5. Hey, that equals 10. Let's connect everything. Boom. Just like that. If I put in all of the lone pairs to make everybody happy, we are going to find out that there are 2, 4, 6, 8, 10, 12, 14 electrons. So that is not going to work for us. So we need to get rid of some electrons, toss in some multiple bonds. Can hydrogen have a multiple bond? No, it cannot have a multiple bond. So we know that the multiple bonds need to go between carbon and nitrogen, and that will be my structure. And as we see on that center atom, carbon, there are no lone pair electrons, 0 lone pair electrons, so this molecule is linear. Now, it asks you for the bond angle. Well, that's the angle between the atoms on the central, between the atoms connected to the central atom. What's that angle? It's 180 degrees. Okay, you can go ahead and pause the video, try those other two. And all right, here are your answers. HCN, we said, is linear, 180. pH3, trigonal pyramidal. And seesaw. Seesaw. Okay. And then a couple of more. We got ozone, which is an interesting one. Okay, if we draw the ozone molecule, we got 3 oxygens combined. If you do the valences, add up the valence electrons correctly, you're going to find that there's actually a double bond between 2 of the oxygens. And you'll notice that there's a pair of lone pair electrons on that central oxygen. These electrons force these oxygens downwards to give a bent structure. Okay, and a bent structure has a 120 degree angle. And let's do one more, and it's going to get a little bit goofy here. Methanol, CH3OH. Now sometimes you're going to have to do organic compounds. Okay, and this is really not that difficult. We just drew methane before, and that was kind of like this. The only difference here is that we are going to have an oxygen off of this atom that's going back into the page. Okay. And now think about what that oxygen is. That oxygen has 2 lone pair electrons, right? So it needs to have its atom connected to it, which in this case is hydrogen, bending as well. It's got to bend as well. So if the oxygen is going back into the page, maybe we can draw that oxygen or that hydrogen bending back towards us. So we can think of the oxygen going into the page, into the screen, and then this hydrogen right here coming back out into the screen. Coming back out into the screen at you, shooting at you, as well as this one coming at you. All right, that's methanol. There you go. That's VSEPR. Okay, we're going to do a lot of molecular modeling with that. It's kind of fun stuff. It's like Legos with chemistry.